Okay, so we are now in entering section 4.3. We covered 4.2, which introduced the notion of a discrete random variable. Today we're going to talk about the notion of the expected value or the expectation of a random variable. Let me remind you first what a random variable is. So last time we covered section 4.2. So they had the notion of a discrete random variable, which we defined to be nothing more than a function called x on the sample space. And we associated to this this notion something called the PMF, the probability mass function, which was given by P of x, which is the probability that the random variable takes value x. And this is by definition the probability of an event. And what event is that? It's the event we take the set of value, the inverse image, the pre-image of x under the random variable. That's the set of values in S, elements of S, which under the function map you to x. Okay, so that's what it is. And then there's also the cumulative distribution function called the CDF, and it's given by f of x, capital F of x, and that's the probability that x is less than or equal to x. And you can rewrite it in the discrete variable case where we are, which we're in, as the sum of P of A, where A is less than or equal to x. Okay, so those are the basic definitions from last time. And today I want to talk about the notion of expected value. Okay, so 4.3 is expected value, also known as the expectation. It is a number that you associate to a random variable. So you start with a random variable. And again, all our random variables in this section are discrete. That's a function, again, from the sample space to the real numbers. And we define the expected value of x is given by, well, here's the notation. It's capital E square bracket x. And it's by definition, this is the definition of it, you sum up over all values in S, x times P of x, where P is the probability mass function. Of course, you only need to sum up over those x's such that P of x is not 0, because if P of x is 0, that contribution to the sum doesn't really matter. There's no contribution to the sum. So you can think of this as a kind of weighted average. That's the way to think of it, as a weighted average. Okay, I'm going to do some examples now to see why it's like a weighted average. So here's an example, a dice roll. Okay, so you're going to roll a six-sided fair dice, and x will be the value of the die on a single roll. So what is that? Well, the value, so we can compute this expectation. The die can take value 1, 2, 3, 4, 5, or 6. So if it takes value 1, the probability of getting 1 is 1/6, of course. In fact, this is the case of equally likely outcomes. You can get a 2 with the probability of 1/6, so we can multiply by 1/6. It's x times P of x, remember, plus 3 times 1/6, plus 4 times 1/6, plus 5 times 1/6. which is the same thing as 1 plus 2 plus 3 plus 4 plus 5 plus 6 over 6. So this is actually the average in this case, and this is going to give you a value of 3.5. How do we interpret this? So suppose we roll the die. This is an interpretation of this number. So suppose we roll the die n times, and then we compute the average of the rolls and compute the average of all the rolls over the n times. Then as n grows, this average tends to 3.5. That's what this is going to. This is actually a theorem. It's called the law of large numbers. We will get back to that later in the course. So that's one way to interpret what that 3.5 is. Okay. Okay, I'm going to talk about another example, which is American roulette. There are two kinds of roulette, basically, the European version and the American version. I'm going to talk about the American version, roulette. I spelled that wrong. Okay, so how does roulette work? You bet $1. There are two ways to bet. I'm going to talk about the idea is a roulette wheel in American roulette has 38 pockets. A ball spins around the wheel and eventually lands in one of the pockets. And let's number the pockets 1, 2, 3, maybe through 38. It doesn't really matter how we number them for the calculation. Now if you bet $1, two things can happen. If you win, the payoff is $35. And if you lose, you'll lose your money. So the payoff is minus $1 if you like. You lose your money. Okay, so what's the expected value of the game? So what is X? X is the monetary value of a $1 bet. Okay, and actually the sample space, you can view it as the numbers 1 through 38 here. So suppose you put your money on any number, fixed number, and we compute the monetary value. Okay, so what is the expected value? The expected value is, well, if you win, you get $35, but the probability of winning is there's 1 out of 38 pockets, so it's 1/38. And then if you lose, you get it. You lose $1 minus $1 times 37 out of 38 possibilities. So I'm doing the calculation, over the entire sample space. You lose. So whatever, if you say bet on 2, then you'll get $35 if 2 shows up. But for every other value, you'll lose $1. So that's what this calculation is showing. 37 out of 38 times. And so if you compute what this is, this turns out to be minus 1/19 of $1. So that is each dollar bet stands to lose on the average of minus 1/19 of $1. Okay, so that's the expected value of roulette. Okay, great. Okay, so my last example for today, example 3, concerns having children. So suppose we have two families, two couples, let's say. Couple 1 has kids until, it makes babies until 2 boys are born. And couple 2 has kids until either 2 boys or a boy and a girl are born. Okay, so what I want to do is I want to compute the expected value of each one of these random variables. So I have to explain what we're doing. Okay, so let's get started. So I'm going to consider first the case of couple number 2. That's sort of the easier case here. So what about couple 2, right? Well, we're assuming the probability of a boy is equal to the probability of a girl here is 1/2. You either have a boy or a girl. Okay, so now what are the outcomes? Well, if we're talking about couple 2, here are the outcomes. So the sample space is going to be, I'm going to put it in a column. The couple could have a boy, then a girl, or then a girl, then a boy, or then a boy, I think I misstated couple 2's goal. Let me start over. Okay, so couple 1 has kids until 2 boys are born. Couple 2 has kids until both a boy and a girl are born. Okay, that's the question I want to answer. So I want to compute the expected value of the number of children of couple 2, right? So X equals the number of children that they have. Okay, so here are the possibilities. A boy, then a girl, then they're done. A girl, then a boy, then they're done. They stop as soon as they have children of both genders. You could have a boy, then a boy, then a girl. You could have a girl, then a boy. You can have a boy, then a girl. Or you can have a girl, then a boy, and so on. Now, what are the probabilities of in each case? Well, having a boy is probability 1/2, and then having a girl is probably probability 1/2. So the probabilities multiply because we're assuming that they're independent events. They likely are. Similarly, in the next case, you get a quarter. In the next case, it's a half times a half times a half is an eighth. Then you have an eighth. In the next case, you have a 16th, then a 16th. You see the pattern. Okay, so now let's compute. So the probability that X is a half is X is 2, sorry. There are 2 cases when the number of children is 2. It's a quarter plus a quarter, which is 1/2. The probability that X is 3 is the case boy, boy, girl, 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 boy. That's an eighth plus an eighth, which is 2/8, which is a quarter. The probability that X equals 4 is similarly, it's going to be 1/16 plus 1/16, which is 2/16 or 1/8. So you can from this we can compute the expected value here. But before I do that, notice that the probability that X is n is a positive integer, bigger than or equal to 2, is going to be equal to what? I claim it's 1/2 to the n minus 1. Okay, so that's where it is. You can check that for the first few cases. That's where it is. Okay, so now we know what the probability mass function is. This is going to be giving, this is little p of 2, this little p of 3, and so on. Okay, I need to save the screen and continue. Okay, so let me make space. Okay. So now what's the expected value of x? This is again couple 2. So we have to take 2 times the probability mass function at 2 plus 3 times the probability mass function at 3, and so on. There are no other values that occur. And so this is going to be given by 2 times a half, because we saw that p of 2 is a half, plus 3 times a quarter, plus 4 times an eighth, etc. And you can actually write out what this is. It's the sum, if you write it in sigma notation, and it's important we do that, it's the sum n equals 2 to infinity of n times 1 over 2 to the power of n minus 1. So I want to compute what that is for you. Amazing, we can actually compute the sum of this series in the following way. Okay, so here's how you do it, right? So remember that 1 plus x squared plus x cubed, all the etc. It's a geometric series. It's 1 over 1 minus x. Here I'm assuming that minus 1 is less than x is less than 1. And indeed, we're going to see that x will be a half in our calculation later. So let's take the derivative of both sides. So the derivative of the left-hand side, the derivative of 1 is 0, the derivative of x is 1, derivative of x squared is 2x, then we get 3x squared, and so on. And the derivative of the right-hand side is the derivative of 1 over 1 minus x, or 1 minus x to the minus first power. By the power rule of differentiation, that's 1 over 1 minus x quantity squared. So the derivative of the left side is equal to the derivative of the right side. Okay, so now you look at this, and you note that this left-hand side is the sum. N goes from, well, I'm going to write it in a slightly funny way. So you can think of this as 1 plus the sum as n goes from 2 to infinity of n x to the n minus 1. And the reason I did that, I wrote it in this funny way, is because we have a similar expression up here. So what we see is that this 1 plus the summation is, we can compute what it is. It's 1 over 1 minus x squared. So I'm going to substitute now into the expression x equals 1/2. And what do we get? So we're going to get 1 plus the sum, n goes from 2 to infinity, n times 1 over 2 to the n minus 1 is equal to 1 over 1 minus 1/2 squared. So that's given by 4 on the right side. So we see that 1 plus the thing we want is 4. So this thing that we want is given by 3. So the expected value is 3. Now in this case, this is couple 2. They're happy to have the number of boys and the number of girls that I have is symmetrical in this case, as you saw, because they have boy, girl, girl, boy, 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 girl, 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 boy, etc. So one could expect them to have 3 halves girls. The expected number of girls is 3 halves. Is equal to 3 halves, and likewise the expected number of boys is 3 halves. So that's the calculation for couple 2. Okay, so the total number of children they have, the expected value is 3. Now let's go to couple 1. Now remember, couple one has to have two boys, right? They keep having kids until they have two boys. So what are the outcomes? Well, they could have two boys in a row and then they're done, and the probability is half times a half or a quarter that they have two boys in a row. They could have girl, boy, boy, but that would be 1/2 times 1/2 times a half. That would be an eighth. Or they can have boy, then a girl, then a boy. That would be an eighth. Or they can have, and that's it, because that's the only two possibilities when they have two kids. This is two kids. This is three kids. These are the only possibilities for three kids in couple one's case. Now, what about four kids? If they have four kids, they could have two girls, then two boys, then they're done. Or they could have a girl, then a boy, then a girl, then a boy. Or they can have a boy, a girl, and a boy. And that turns out to be it. So, and the probabilities in each case are 1/16, 1/16, 1/16. Okay. You can start seeing the pattern. If they have five kids, there are going to be four cases in five kids. So now what is the PMF in this case? The PMF is P of 2 is a quarter, because of that's the only there's only one case of two kids, BB, and that's probability 1/4. P of 3 is an eighth plus an eighth, which is 2/8, which is a quarter, but I'm going to write it as 2/8. But P of 4 is 3/16, and P of 5 is 4/32. You see the pattern. Okay, and the expected value of the number of kids in this case is given by 2 times a quarter plus 3 times 2/8 plus 4 times 3/16 plus 5 times 4/32, etc. And you can write this as the sum of n. So n is going to go from 2 to infinity in this case. The sum as n goes from 2 to infinity of n times n minus 1 over 2 to the power of n. And I have to compute this for you. So this is what I need to compute. Okay, and we're going to get a different answer than in the case of the previous couple 2. Okay, so I want to compute this sum, and I'm going to do it like I did the previous sum. So first of all, let's recall that what you get when you sum up powers of x, you're going to get plus dot dot dot. It's 1 over 1 minus x. That's the geometric series. If we differentiate both sides, let's recall that you get 1 plus 2x plus 3x squared and so on, dot dot dot, is 1 over 1 minus x squared. We can differentiate one more time, and we're going to get the derivative of 2x is 1 times 2 times x, and then I'm sorry, that's not correct. It's 1 times 2 plus 2 times 3 times x plus 3 times 4 times x squared, and so on. The right side of the calculation is the derivative of 1 over 1 minus x squared, and that's 2 over 1 minus x cubed. You can easily verify that that's the derivative. Now the left-hand side is given by the sum of n times n minus 1 x to the power of n minus 2 as n is going from 2 to infinity. You can easily check that that's what you get, right? That the left-hand side of this, the left-hand sum is that. So we see that this is true. And I'm assuming that absolute value of x is strictly less than 1 for this to be correct. Okay, so now I'm going to take x equals a half. If you take x equals a half, you're going to get the left side is going to give me the expression we want. But what about the right side? The right side So that's going to give me n times n minus 1 over 2 to the n goes from 2 to infinity. But what is the right side? The right side, you plug in x equals a half, you can get 2 over 1 minus a half cubed, which is 2 over 1/8, which looks like it's 16 to me, right? Okay, so that's right. You get 16 for that. And I did something wrong here. What did I do? Oh, I know what I did wrong. This is not 2 to the n, this is 2 to the n minus 2 that we're getting on the left side. It's not what's on the top of the screen. So in order to get what's on the top of the screen, we multiply this expression, everything in sight, by 1 over 2 squared. That'll convert the 1 over 2 to the n minus 2 to the 1 over 2 to the n. And if I multiply the right side by 1 over 2 squared, I get 16 over 4, and I get 4. That'll be the answer. So the expected value of the number of kids is 4 in the case of couple number 1. And what does that mean? That means since 2 boys are born, they're always going to have 2 boys. That they keep having kids until they have 2 boys. That also means that the number of girls, the expected value of the number of girls, is also 2 in this case. Okay, so that's it for this example, and that's it for it today.